Hello everyone! In this video we will continue to examine topic 7.1 discrete energy and radioactivity, and in particular we will continue to unpack the three main mechanisms of radioactive decay. In our last video we introduced the idea that there were three main mechanisms or ways in which unstable nuclei can undergo radioactive decay. And these were named after letters of the Greek alphabet in the rough order of their discovery and importance. There are more mechanisms of radioactive decay, but these are the three main types. We introduced alpha decay, where alpha particles were later discovered to be helium nuclei, and these are, relatively speaking, massive and highly ionizing radiation, but with low penetrative power. Radioactivity rather than radiation would be the correct word there. The second main type we're going to discuss is beta decay, and beta decay comes in two varieties, beta minus and beta plus. In beta minus decay, the parent nuclide of element X with nucleon number A and proton number Z increases by its proton number by 1, but keeps the same nucleon number. Another way of describing that is that a neutron becomes a proton in some sort of meaningful sense, and we'll talk about what that means in a second. It emits the beta particle, and it also emits another particle, which we'll talk about in a moment. Okay, so this beta particle was discovered to be negatively charged. It was discovered to be much lighter than alpha decay, and as it turns out, that beta particle is in fact simply an energetic electron. But it's important to recognize that in beta decay, it's not an existing electron that is simply being released from the initial atom or nuclide X. What is happening is that a neutron inside the nucleus is transmuting into a proton and an electron. It's becoming a proton and an electron. Now, it's important to recognize that this strikes us as sort of indicating that the neutron was simply a proton plus an electron to begin with, but that's not the case. This is an actual nuclear reaction, what is known as a transmutation, where that neutron, with its own properties, becomes a proton and an electron. And the emission of that beta minus particle, otherwise known as an electron, is the outcome. The effect is that the element keeps the same nucleon number, but a neutron has decayed into a proton and electron, and so it's important to recognize that that X element changes elements. It becomes Y. It actually increases its proton number, so it moves up the periodic table by 1, although without changing its total number of nucleons. This electron, in context of radioactive decay, is often indicated with the symbol beta, or beta minus, but it can also be indicated with the symbol electron. And in fact, the IB likes a bit of terminology that bothers me on a fundamental level, or a bit of notation anyway. The IB likes to write it like this. 0 doesn't bother me at all. If this is an electron, then it has a 0 nucleon number. But the IB really likes to write a little -1 here as a way of sort of indicating how the proton number is going to balance. But that -1 is kind of meaningless. It's not really, there's no such thing as a negative proton. That's not what this is. So, I would hesitate before recommending its use, but you will see it. Okay, so this -1 simply indicates that the total proton number has changed so that you get 91 plus -1 equals 90 here. So that's this emitted electron, that beta minus particle. And then there's also another particle, and actually the discovery of this particle is worth discussing at a later point. But this extra particle is an electron antineutrino. So the first thing to note is that this particle is a neutrino. So it is a neutral particle. It is very, very low mass and largely interactionless. As it turns out, there are trillions of neutrinos passing through your body, known as solar neutrinos, from the nuclear reactions in the center of the sun every second that you don't notice because they're very low mass and they almost never interact with particles. Our best neutrino detectors are massive. They tend to be buried underground, and they detect somewhere between 2 and 100 events per year. So very, very, very low interaction rate. And its discovery is actually an interesting story for another time. Neutrinos come in 3 varieties, which we'll discuss in topic 7.3. This particular variety is an electron antineutrino, so that's what that little e is doing. And it is also an antineutrino, so it is our very first antimatter particle, which we will also discuss in more detail in topic 7.3. I include it now simply as a way of indicating what this particle is. Hopefully I will get to answer your questions about antimatter and this particle in general a little bit later on. For our purposes in this section, though, I would encourage you to focus in on the beta particle, as that is why this is named beta decay. So, for example, you might have thorium with a proton number of 90, beta decay into palladium with an atomic number of 91 through this mechanism. Just like in alpha decay, you can predict questions that ask you to identify the missing particle. So if you're given this, and you're given this, and this is a blank, you should be able to identify that as a beta particle or as an electron. In almost every case, both are acceptable, or they should be anyway. Other things to know about the beta particle itself, that is that high energy electron, is that it is very light. The mass of the electron is much, much smaller than the mass of the helium nucleus, that is alpha decay. It has sort of a middle level penetrating power because it's significantly smaller. It's stopped by about a few millimeters of lead. So you do need some sort of barrier, but a few millimeters of lead will do it. And I think something on the order of 30 centimeters of air. It is sort of middle ionizing power, so about 100 ions per millimeter of air, and it is negatively charged because it is an electron. Things to know include the fact that if it were me, I would be much more scared of direct contact with a beta emitter than I would with an alpha emitter, because even though alpha emitters are much, much higher energy and can do more damage, a beta emitter can penetrate the skin. And as a result, they can do some serious damage if you're exposed to them for too long. And we'll talk about sort of the damage and health effects of radioactivity and radiation at a later time. So that's beta minus decay. As you might indicate, or as you might know, simply from this nomenclature, there's also a thing as beta plus decay. Now, just side note here, you almost never want to refer to this sign as a minus sign. This is just a traditional name. So beta minus decay as being beta plus the negative sign just is what it is. But we call this beta minus, and we call this beta plus. So let's analyze what's going on in beta plus decay. In beta plus decay, a beta plus particle is emitted. What happens to the parent nuclide, X, with nucleon number A and proton number Z, is that A stays the same, just as in beta minus decay. But instead of incrementing up by 1, the proton number decrements by 1. It goes down by 1, which indicates that in some meaningful sense, a proton is becoming a neutron. That is, one of the nucleons in that original nuclide that was a proton has transmuted into a neutron and a beta positive particle. Now, what is a beta positive particle? A beta positive particle is not a proton. It is, in fact, an antimatter electron, or an antiparticle of the electron. As I mentioned before, we'll discuss antimatter in significantly more detail in topic 7.3, but for now, you can think of an antimatter particle as simply being a particle with sort of the opposite properties, except for mass, of the electron. So this particle is known as a positron, and it's written as E+. It is the same size as an electron, and effectively sort of the equivalent of the electron, just with opposite charge, and as it turns out, a couple of other properties, which we'll get to in due time. So this beta positive particle is actually a relatively common mechanism of beta decay and of radioactive decay in general. The accompanying particle, by the way, is no longer an electron antineutrino. It is simply an electron neutrino. And that is no accident. This symmetry here, where you have an anti-electron and an electron neutrino, and you have an electron and an anti-neutrino, or electron antineutrino, is not an accident. We'll discuss that pattern later on. So this positively charged plus E beta particle also has the other properties of beta minus decay. It is very light. It has a middle strength penetrating power and middle strength ionizing power. One thing to note here, it renders it much clearer that what is going on fundamentally when that proton transmutes into a neutron plus a positron is not that the neutron was simply made up, as it seemed like it might have been up here, of a proton and an electron. That is not what is going on. This is a particular kind of transmutation, that is distinctive of nuclear reactions.